We propose and study a model for flashing subdiffusive ratchets in viscoelastic media like dense polymer solutions or cytosol of biological cells. The medium degrees of freedom are modeled by auxiliary Brownian particles elastically attached to central Brownian particles. Some of these auxiliary particles are extremely sluggish. They imprint the memory about position of central Brownian particles and cause subdiffusion and anomalous transport on sufficiently large time scale. At the same time, this anomalous transport is combined with inertial effect and even ballistic diffusion and transport at a very short time scale. Just a handful of such auxiliary particles suffices to model subdiffusion on practically any experimentally related time scale. Our setup is fully equivalent to generalized Langevin equation, where the memory kernel and random force of environment are related by fluctuation-dissipation relation at the ambient temperature of the environment. By properly choosing parameters of our model, we numerically very reliably integrate a model with a power law decaying memory kernel, which corresponds to so-called fractional Langevin equation. Flashing of the potential, either random or periodic, violates the symmetry of thermal detail balance and induces directed transport. This transport is anomalous and therefore it is characterized by subvelocity rather than normal velocity. The diffusion is asymptotically anomalously slow, independently of the height of the potential or the frequency of the flashing. At the small time scales, diffusion and transport remains ballistic reflective inertial effect. Asymptotically, we show also that our setup, our modeling is fully ergodic. One of the most striking manifestations of the inertial effect are the resonance and synchronization feature in the case of periodic flashing. Subvelocity shows in its dependence on the frequency of flashing multiple resonance features. The resonance occurs between the frequency of external driving and the frequency of nonlinear oscillation within one potential value. So, one-to-one synchronization is responsible for optimal transport in the intuitively expected negative direction. At the same time, two-to-one synchronization is responsible for the optimal transport in the opposite counterintuitive direction. Another remarkable feature of our model is the persistence of anomalous transport at zero temperature. The direction of transport can depend on either on the character of flashing. It can occur in different directions for the periodic flashing or for random flashing of the same frequency. The subdiffusion coefficients vanish linearly with the temperature, and this means that very small temperature our transport possesses a very high quality and is low dispersive. We expect that highly non-trivial results obtained in this work will stimulate a further cross-fertilization between the fields of anomalous diffusion and transport and the field of fluctuation-induced transport and diffusion.